Hi everyone. Today we're going to be doing homework 2 part B, in which it has 3 parts. Part 1 is to express the heat diffusion equation from part A1 as an algebraic equation via the Crank-Nicolson differentiation. Part 2 is use the von Neumann stability analysis show that the Crank-Nicolson differentiation scheme is stable regardless of the choice of R. And then for part 3, we're going to simulate the time-dependent response of a uniform bar initially at 20 C after its ends are raised, then maintained at 50 and 80 C respectively. Discretize the bar with 100 time-dependent temperatures and solve the equation from part 1 using scipy.linalg.solveBandit for R equals alpha delta T over 2 delta X squared equals 2 over 2,500 time steps. Plot the simulated results in 100 time step intervals. So before we start going back to part A into part 1, let me explain what we're going to be doing today. So for part 1, we have a Crank-Nicolson method differencing, which is right here as shown on the screen. And what it really ends up doing is it's averaging out. It's implicit differentiating, which allows us, or turns us into a matrix, or allows us to solve using a matrix. So I'm going to first, let's see, where is it? I'm going to first express it as an algebraic equation for Crank-Nicolson. Then I'm going to use von Neumann stability method, or stability analysis. And then, before we start coding, I'm actually going to write a matrix up on the board, as it's a lot easier to explain the code part of this portion with being shown the matrix step. As we don't technically have to show it for part 1 and 2, it makes part 3 a heck of a lot easier. So I'm going to get up on the board and start with part B, part 1. Hi everyone. As you can see, I have moved us to the board. This is a different room than I'm used to, so I'm still working out the kinks. And there's also a computer board right in front of me, so if you see me trip or stumble at any time during this video, that's most likely what it is. So as you can see here, I wrote the diffusion equation up here. We have dt over dt equals alpha d squared t over dx squared, which we can end up, as you saw in our previous video, turning that into what we see here. This is the Crank-Nicolson method of differentiating. So first, as you can see here, is we have our alpha over delta x squared, and then we have our fun value over here, which we're averaging, to then get our next time cycle. So, the first thing we're going to do is we're going to move this delta t over, and we're going to call this r. Well, at the same time, we're going to take this 2 divided by 2 power over these values, and we're going to basically plug that in with r. So over here, I'm going to write that r equals alpha times delta t over 2 times delta x squared. That way, I can erase all these terms, and we're going to put that with a fun letter called r. So the next step of what we're going to do is we have our knowns and we have our unknowns. Our knowns are our current time, our n, and our unknowns are going to be our n plus 1. So we're going to separate these values. So let's get at it. So our n plus 1s, we are going to have, let's see, this is an n plus 1, and everything has an r. So make sure I do this so it's right. Every value has its r. So, as you can see, we have a n plus 1 and a n. I get n plus 1 and an n, and we have our n plus 1 and we have our n's. So what we're going to see here is we're going to see a -2 or 2 plus 1 or minus 1. So we're going to put our n's on this side. So we're going to have, let's see, we're going to start right here. We're going to have t and j, and then Tn times r. Sorry, let me rewrite this. And again, if it's hard to see, as it looks like it is kind of on the board, I'm going to enunciate everything I'm doing. So Tnj, as we pull that over, let's see, plus r times Tnj plus 1 minus 2 Tnj plus Tnj minus 1. And then on the other side, we are going to have our illustrious t, j, n plus 1, and we're going to subtract it. So minus r, and we have t n plus 1 j plus 1. Let's see, we're going to pull this right over here. And basically, I'm putting this negative sign in front of the r for this entire term. That was my neck. Minus 2t n plus 1 j. Forgot this j plus 1. Plus our t n plus 1 j minus 1. So now what we're going to do is we're going to basically put our r values in here. And we're factoring in terms of our tj's, I believe. So this is essentially our algebraic equation, but we can make it a lot prettier. So we would have we would have t j plus 1 n r times tj plus n minus 2r minus 1 to then for t n j, because we have a minus 2r of t j n, we still have our positive 1, plus our t n j minus 1 times r. And then over here, we do the same thing. Again, with respect to just a negative r value. So first we're going to start with our plus 1. So we have negative r times t j plus 1 n plus 1 plus, now we're going to do, because it's a minus, plus 2r, and then we're going to do, because of the, this is a value, we subtract it over here because it was a negative. Because this is a negative r, it turns into a positive. So when we factor in, plus 1 times tjn, and then minus r times tj minus 1 and plus 1. And plus 1 and plus 1. Okay, so what we have here is our algebraic equation. Or just to make sure you can read it, it's tiny, but somewhat legible, is our algebraic equation for our Crank-Nicholson method, in which we're going to code out and show that it's viable in the future, but we're also going to derive that. So what I'm going to do next is I'm going to erase the board, and using the von Neumann stability method, Newman or Neumann, I don't remember exactly which one, I am going to show that it works for all values of r. So I erased the board like I said I would, and I rewrote our general equation. And if you can see over here, I know it might be kind of hard to see, this is something we actually worked with in homework 2 video 1, which this part is going to see very, very familiar, or part A, excuse me, due to the fact that it's, again, a von Neumann stability analysis. So first and foremost, we need to select r, in which we have that r equals alpha delta t all over 2 times the delta x squared. That way, again, as we just did, we can erase this value and replace it with r. So the next step of this is we are going to, at the same time, forgot this n up here, we're going to take this value of tj to the n across while we replace our tj plus 1 and our tj minus 1 with e. Well, for example, for tn to the j plus 1 equals e to the ik delta x times tjn. And then for j minus 1, it is e to the negative k delta x times tnj. It's the same thing, just one is a negative step, one is a positive step, depending on which direction or exactly which position our value is. So we're going to take this over, and we end up getting, right over here, t j n plus 1, and so my arm doesn't fall off, equals t j n times r to this funky business. So we have tn plus 1 times, because it's a j plus 1 is going to be e to the I k delta x plus, excuse me, and I forgot this is because it's a j. Because what we're doing is we're replacing everything with either tjn plus 1 or tjn, depending on what n value it is. We're just rewriting this value without terms of j plus 1, or without terms of j minus 1. Minus 2tjn plus 1 plus, let's see, it's going to be e I k negative x, we're going to get a negative times t j to the n plus 1. And now we're going to add, which is just this fun little piece again. So t n j times e to the I k delta x minus 2 times t n j plus, let's see, t n j. See, I messed up. Oh, no, I didn't. No, I didn't. I keep thinking I'm messing up because I'm missing the j's. That's the whole point of this situation. T n j times e to the negative I k delta x. Oh, that's not where parentheses should go. So, now that we have everything situated like this, what we need to do is basically conglomerate our values. We're going to want to move something over our tj to the n's over here, and our tjn plus 1 over here, and our tj's to the n we're going to keep over on this side. And while I see I made a mistake again, this should not be a multiplication sign. This should be an addition sign, as we factored it over by addition. So what we want to do, and something we also need to make note of, is that, actually, I'm getting ahead of myself. Let's factor everything over. So, this is what we just did. We have tjn plus 1, and we're going to do plus, or excuse me, minus this value. We're just going to do with r for now, with respect to r. So this will be tn plus 1 j e I k delta x minus 2 tjn plus 1 plus e negative I k delta x times tjn plus 1. I know this is ugly. This is just so we can get to the next step. Then we have tjn r, and then this fun bunch over here. We should have t and j e I k delta x minus 2 t j n. It's too big of a j. Oh, there's two erasers up here. I never noticed. J plus t n j e to the negative I k delta x. Oh, this should be a bracket. And then so should this. So the next step is we want to factor out our tjn's, like exactly what we did in the last step. So, but because we have our r's, we're basically going to factor something in and take it out. While at the same point, the issue, or something that is an issue, let's just factor everything out first. So, we have our tjn plus 1 minus, okay. Then we're going to factor a negative r out. We have e I k delta x minus 2 plus e negative I k delta x. Right? That looks right. And then the same thing over here. tjn plus r. This is just making sure I know. Remember, it's a positive sign. I shouldn't just erase that. It's a positive r because it looks like it. The r, and then we have e I k delta x minus 2 plus e I k k delta x, which is a negative. And something to remember, much like last time we did this, is that basically, if we have e to the negative I k delta x plus e to the negative, or plus positive, excuse me, I k delta x, we actually end up getting equals 2 cosine k delta x. And if you want to look for the derivation of this, I believe it is in homework 1, I want to say part 4, part D. I think that sounds right to me. So what we have here is where you're going to have our t, j, n plus 1, to then our negative r, to then our 2 cos k delta x, right, minus 2, we're going to move this over there, equals our t, j, n, to then our r value of 2 cos k delta x, and boom. So the next thing we want to do is we're going to want to evaluate these. However, I don't exactly have enough room on my board, so I am going to erase, move some of our things up, and I will be right back. So, as you can see, I didn't erase, and that's because I actually realized I made a mistake. So what mistake I made is when I was factoring out my tjn and my tjn plus 1, I actually lost a value, because this in itself, our tjn plus 1 tjn, is just a 1 value of itself. So essentially what I lost here is a 1 minus r, then tjn plus 1, and then over here, I lost a 1 plus r, then a tjn. So I should have put it down here. Son of a gun. So actually, let me just do that over here as I erase this whole thing. So we can do this as I talk. So we have our 1, hard to see, but it's there, and our 1 plus r. So the next thing we want to do is we are going to evaluate these as a ratio. A ratio. So what that means is we are going to want to put tjn plus 1 by itself, and then have this over here. So we have, and I'll show you what I mean, we're going to have tjn plus 1 equals 1, excuse me, this, we have tjn times 1 minus r, then a 2 cosine k delta x 2 minus 2, in which what we really could do is factor out this 2 and move it across, which actually we're going to do it right now. Actually, no, it's fine. And then over 1 plus r, 2 cos k delta x minus 2. And what we're actually going to do is we're going to create a new variable. And we're going to call this variable z, because z in physics and other stuff is a compressibility factor. And I think that makes sense. So z is going to be, we're just going to leave it like this. Our r times 2 cos k delta x minus 2. And the reason we're doing this is because we know that something that's, oh, messed this up here. So cos x can get no larger than 1. That's its max value. And if we factor this out, we would end up getting 2r and then cos k delta x, like that, minus 1. And we know that this internal term, no matter what, because again, erase the wrong thing, excuse me. K delta x, this internal term, or cos k delta x minus 1, if the max value that's going to be is 1, well, eventually cancel itself out before it ever reaches this 2r to multiply that factor. So that's why we're going to leave it like this, because we could factor it out, but essentially we get the same result. So we end up getting t j n plus 1 equals t j n 1 minus z over 1 plus z. And let me erase this down here. So what this term actually means is that no matter what your z value is, so because z includes r, so no matter what your r value is, this value is, or tjn is never going to be multiplied by something that is greater than 1. Because let's say we have 3. 1 minus 3 over 1 plus 3. The bottom, the numerator, is always going to be greater than, the denominator, excuse me, is always going to be greater than the numerator, showing that this value, this z, or this term, will never be greater than 1. Meaning it's never going to shoot our tjn up to infinity like you saw in our previous video of homework 1, where the stability, and when we coded it out, really just moon rocketed it to something to the 300th power. So by showing this, and by using the von Neumann stability method, we were able to see just how we can calculate and why this works and will never really cause the stability issues that we saw previously. So I think that actually answers part B. So what I'm going to do is I'm going to write a matrix on the board and then kind of explain how this affects our code, which will be the next part of the problem. So before we start talking about the matrix I drew, I wanted to mention that what we just solved, or tjn plus 1 equals the tjn to the ratio of 1 minus z over 1 plus z, is again only valid for when z is positive. Because if it's not, it really throws off the whole feng shui of this argument. So I really wanted to make sure that was written down and I was explicitly stated. So the next part I wanted to mention is this matrix I drew. So what this matrix really represents is this is what we had when we separated our n plus 1s and our n's, and I just didn't feel like writing the rest of the n portion. So what we have for a matrix is technically what's called a sparse matrix. So we have a 0, 0, 0. So what this is essentially a straight diagonal across a matrix where we only have 3 different numbers. Well, 2 values essentially. We have in our middle our 1 plus 2r, like what we have here, and then we also have our negative r's, which you can see here and here, which are on other sides of the position. Because what we're talking about is the position. So for example, at position 1, we have 1 plus 2r in the middle. At position 2, we have 1 plus 2r in the middle, because it's the regular position. So for example, at position 1, what we have here is on both sides. So at basically 0 and at 2, we have negative r. And the same goes for position 2, position 3, all the way to position n for who knows. And then it's the same, well, and then what we want to do is we want to multiply, and we want to be able to get out our next tn, our next time interval. So what that would end up looking like is with this matrix multiplication as we have here, we would end up having, let me double check. If we were to start at 1, be like I don't exactly remember, but what we're going to do is we're actually going to be coding this out in Python, just so it's easier to see. But the reason I'm showing you this is just because it's a little bit easier to figure out where I'm getting these values from when I'm coding. But, all right, so thank you, and I will see you in Google Colab.
All right, now that we have gone over matrices, we can start. So first we're going to create our temperature array. So we're going to do np.full of then n comma r. That's the value we want to fill. Then we want to do our t left. So our left hand of the bar is going to be 50 degrees, and our t right is going to be 80 degrees, as that's the way the bar works. We also want to now start creating our values. So we're going to have a value which is t, and then it's going to be something like this. So t something until I figure out a better name equals, you want to do like an array, so like np.c. What we want to do is np.full. We want our three values that we just talked about. np.full, and we're going to do n comma r. We're going to call this sparse. N comma negative r, comma np.full, and we're going to do size n, and the size is going to be 1 plus 2r. And then our next value is going to be np.full, n comma negative r. And what we're doing here is concatenating something. So our next thing is we're going to do our fig equals make subplots. Forgot the underscore. We also want to do our position of where we are equals np dot arrange, which I know is now spelled with one r after my debacle of last class, which we want to do something like n plus 2, as that's the size we want of our array, because we're going to have two, our specific one on the left and our specific one on the right. And we also are going to want to do, when we start making a graph, we're going to do for I in range of 1 comma 2500, I believe is what it said on the homework. Let's check. 2500, right? Let's see, n's raised to 50 and 80, so our 50 is on the left, our 80 is on the right. And now we are probably missing something, but we can start doing, so important thing to note is when we do x equals plus, essentially you're just adding something in itself. So it's the same as, like, x equals plus 2 is the same thing as x equals x plus 2. But it's easier to do this when you're working with specific values. So I am going to make sure this works. See, there's a syntax with an incomplete input. Let's see, oh. Line 11, this is, doesn't specifically say. So I'm going to be right back and make sure everything works before, see, I enter. Oh, it's indented already, so that's good. Let me get rid of that. I'm going to go make sure everything works, and I'll be right back. So I found that, well, I didn't find, I realized this should be 20, because that's how it's set up. And the problem, as you can see, everything is initially at 20, and we're setting our initial state values. Also, this needs to be underscore, so I realize this is exactly what it is. So now we're going to do fig dot add subplot. And then our x equals position. Our y is going to equal np.row. And then it's going to be t left, not t right, comma t left, and then our name is going to equal 0, but I think I need fancy brackets, I'll be honest. Alright, so now we're going to start with this value. Now we need to create our array, essentially. So b equals, let's see, this will be -1 times 2r, I believe. I will get these atrociously wrong. And now we need to set our different values. So we're going to have b to then, I think it's like 1 to 1. We're going to have, let's see, why does that work like that? It makes no sense. Anyways, I'm just trying to make it where, anyways, I digress. That's going to equal value. We're going to have our b to a, say a 0. It's going to equal like b to a 0 should equal negative r times something specific. Same with b to a negative 1 value, because we're going to want our specific set up for our n's. Equal plus equals, and then we're going to want a few other things, I believe. So let's see, does this work? Alright, so this actually seems to end up working, but this is invalid syntax because there's nothing there. Let's see. I am also going to be equal b. I don't know. I'll be right back because I have what's set up right. I'm just getting lost. Well, I'm not getting lost. I keep forgetting exactly matrix multiplication wise what values am I specifically needing. So I've kind of versed myself a little bit better, and I think I have believed what we're doing. But while also going through there, I realized this should be a f, so it actually has a name. F, and then this should be add scatter. The subplot's already made. So first, our b is going to be 1 minus 2r times t, because our t is our array up here. Let's see, what's the issue? It is, okay. Then we're going to have our b to the 1 to the 1. That makes no sense. So you want to the 1 to the minus 1, because we want our values from here to there. Equal plus our value, so we're going to do times t to the 2 dash and on, and we're going to do this again, where it's going to be, oh, it's not right, it should not. So that equals t to our negative 2, see, our negative 2 dash and on. And we want to multiply this by, again, r times this value. We want to do this by an r times this value. That way we have our specific values for our temperatures on our different sides of our original. Why does this look so ugly? Oh, wait, this is probably right. Yep, realized it was wrong. So now we're going to do, we have our b0, I think. We're going to have our b negative 1. In which, no, that's not what we want, my bad. In which we're going to be calling back our t left and our t rights. So it's going to be our t left equals minus r times our t right, I believe. And now we're going to do this, where we're going to do, let's see, what's it called? Oh, we need to solve, duh. So solve. This actually needs to be within this because we're solving with it. Solve banded equals 1 comma 1. Our AB is going to be, oh wait, we gotta do that. So we're going to do our AB. Well, this is our matrix. So this might be our T something, and then a B, as this is what we actually want. Now we're going to do kind of what we did in our last one when we were making a class. So for, we're going to do if I percent 100, essentially if it ends in 100, and it's basically an even thingamadoohickey, you gotta do fig dot add scatter, and then x equals position, comma y equals this thingamadoohickey. Then we're going to do mode equals lines, which I actually need to do up here. Name equals, let's see, f think this works. We're indexing it. Let's do it up here. Mode equals lines, comma, expected, well, duh, that makes sense. Let's see. I mean, it says module numpy has an attribute to row, so maybe it's np.r, because it is np.c, so let's try this. No, our attribute r. Huh. So I definitely messed up something then. So what we're trying to do is we concatenate it, now we're going to make it in a row so we can have our math that we can do. Or we've done our math essentially. So that means this is also wrong. Let me get right back and let me see where I made a mistake. I also found a lot of different issues, so we have, it should actually be r times t1 plus 2 times r times t left, and then r times t to the negative 2. Let's see, r times t to the negative 2 plus, oh gosh, 2 times r times that. I also just didn't solve for anything in here. So like, and the main issue, the crux of the issue was it's r, but it's underscore, because of course it is. I always seem to forget the underscores, along with everything else. So, it says, A and B shapes are not compatible, meaning there's something wrong with my T something, 103. Let's see, T something is 103, and then B is something with, this means I'm missing something for why it's a row. Shoot, that's annoying. Yeah, so we know that's 103, like it should be. And then A and B are not compatible, meaning there's different sizes, so there's definitely an issue somewhere. I might need to like concatenate something, or like if I do np dot, let's just try this because I can, np dot r, square to something. Oh, if I go like, maybe that'll work, who knows. Nope, okay, that didn't work. Let me look at, let's see, let's get rid of this now, for now. Maybe I made a mistake somewhere. Let me be right back. So I found a lot of issues while going through this. First and foremost, I found that this should be dot t, that way we actually get in the right form. But this negative r is not right. Well, also, so if we do this, oh, what the heck. So then we also have array must not contain issues. Well, the reason for this, I believe, is that first and foremost, another change is that this should be t left, because it's the left side of the chart, and this should be t right. And I made that mistake twice. Like, what a surprise. T left, T right. The next thing I found is that this is in the wrong order. It should be plus equal, and that everything should have them. And hopefully that fixed my issues. The next thing is that this was not indented correctly, so I have to indent it. But now it's not right, because of course it's not. What we have is our original values. There's something with fig. I run that again. So what happened was I had it down here, and then I hadn't ran it again after I fixed everything. And as you can see, as I've been checking this is right. So what we ended up solving is, so we wanted to simulate the dependent response no matter what the r value is. Because as you can remember for a previous video, if r was anything greater than 0.5, as we proved, it went basically crap sideways. But as we can see here, if we even have an r value of 2, it's still stable. And we can go through all these. Oh, no, that's too much. And as you can see, the temperatures even out. You know, we start at 50, we start at 80, and everything else is 20. Excuse me. So the next iteration At position 40, it's 26. The position after is 37, then 44, and then 50, 56, and then it almost gets up to a steady state, which is really the whole goal of this, is to kind of prove what we had learned and plot the simulated results in 100 time step intervals, which is exactly what this fun guy was doing here. But now that this is over, to say thank you for watching.